Hi, welcome to my video on CUDA programming. We'll talk today about implementing RLE decoding in CUDA. Run-linked encoding, or shortly RLE, is a compression technique. And internally it has a component that is looking intrinsically linear. Yet, besides being linear, it is possible to decompose the algorithm to run significantly in parallel. And in this video, I'll show you how to do that, how to decompress an RLE coded input on a CUDA parallel environment. It will also illustrate how to work with cooperative groups in CUDA and how to use shared memory to accomplish that decompression. Now, let's first start with what RLE actually is. RLE is an old technique, an old compression technique, which was mainly used or heavily used when faxes were popular. That's because a document that is faxed is often largely white space, and to send over many 0 bits just to tell that a line is blank is not very efficient. So compression was used to make actually the sending of the fax quicker and more economically. So using RLE, instead of sending the same character over and over again, we basically send over how many times that a character is occurring. So 4 zeros, and then we send over the 4. 3 ones, then we send over the 3, etc. And in binary, we actually, because we don't need to send over the content or the value of what is counted, because it is basically alternating between zeros and ones, right? But as soon as you are sending gray level pictures, or when you're sending color, then of course that's no longer a 0 or 1 value, and then we need to supply also the values. Now, not every image can be compressed decently with RLE. If you take a picture with your camera, it will typically not be compressed. It could even become a lot bigger. But for things like here, like for instance this type of logo, or for a label on a product that has a lot of common color in the sequences, RLE compression is really doing a great job. Right, so a bit of background for those who are interested in learning about using cooperative groups in CUDA. These are really 2 good sources. Just search for the names on YouTube and you'll find good videos and also good code samples. And if you are more interested in the RLE side of this video, we will show an implementation of RLE decoding, but 2 nice implementations of RLE encoding on CUDA are shown here in these 2 posts. I advise to first look at this one, because it's a bit easier to understand. This has a very nice algorithm that is shown there. A bit more advanced, but a very elegant way to attack the problem. Now, what is all the fuss about, right? What an RLE decoding must do is reconstruct the original sequence. This is a sequence, and actually what we get in is this compressed format. So what the RLE decoding needs to do is explode this to 4, 5, explode this to 3, 3s, etc. Now, all this is based on a series of lengths, right? 4, 3, 6, 7, and a series of values. And that by itself is pretty easy to put in a lot of threads, because you could each thread assign the task to explode that couple of length and value. The problem is, of course, where does the thread need to place all these values? And that's actually after the space taken up by the lower threads. So if you have these values, if you want to place the 6s here, you have to know that you need to start at offset number 13, which is actually the length of this, and the length of this, and the length of this together. And it's easy to understand that all offsets can be calculated by the previous offset and then adding the next length. But of course, this is a very serial way of calculating, and one that cannot be made faster by splitting the work into many threads. Now in this video we will first show a way how this can be approached differently, that enables that splitting in tasks. And then we will show also the CUDA code using shared memory and cooperative group to implement this algorithm. Now, a very classic example of the divide and conquer method that we typically use in parallel programming, and you find it really dozens of times on the internet, is a way to sum a series of values. And in that approach, if you need to add n numbers, you launch the half of that number of threads, and each thread starts with adding 2 consecutive numbers of the series. And then what you end up with is new series of values, half the size, and then half of the threads stop working. The other half is adding again 2 of those numbers. Basically, each number is then the sum of 4 values. And you continue and you continue until you have only 1 thread left that just needs to add 2 values, and you have the final result. We will do something a bit similar to calculate the offsets, but our task is a bit more difficult because remember, we need to have all the offsets, just not a final value. So if we have here like 16 lengths, 16 of those lengths of the sequences, we will indeed have half the amount of threads. And to place the values, you need always the final offset. For instance, thread number 4 needs to know the sum of all these lengths, 0 up to 7. And for that value, it needs to have then 0 up to 8. It's easy to see if you have one offset of the thread that the other one is pretty easy to calculate. You just need one extra addition. So we will handle with one thread actually 2 of the values. Now, the algorithm itself exists of 3 parts. And the first part we call step 0, and that's explained here. And in that step 0, each thread starts with summing just 2 numbers required for the odd offsets. So we will calculate only the odd offsets in the beginning. And at the very end, we will also calculate then the even offsets. But we start with the odd offsets. And what we will actually do is we will add the 2 values, the 2 last values of that sequence. So we need the sequence here for thread 3. We need sequence 0 to 6 to add all together. And the last 2 are actually length number 5 and length number 6. And those 2 we will add in this thread number 3. So thread number 3 will add those 2 values, thread number 4 will add those 2 values, and store that in memory. And then the next step is going to build upon those partial results. Actually, all the next steps are doing something very similar to each other. So the first step was a bit different, but now the next steps are doing always something that is very similar. And what they basically do is that they will use previous result to extend that range of added values. So for instance, again, thread number 3, we had already 5 and 6 added together. And we see that the previous thread is actually having the sum of 3 and 4. So it can use that to extend it, and now we have the sum of lengths 3 up to 6. And the same holds for some other threads that will do similar kind of work. Now what you see is that not all threads are participating in these steps. Only half of the threads are actually doing something. The others are actually already in a state where that is starting with the same length as the one that is calculated. So those 2 now start with 7, those 2 with 3, those 2 with length number 0. So in the next step, and the one after that, we just continue that kind of work. So what you see, for instance, in step 2, this is the next step. In step 2, thread number 2, that's this one, already had the sum of lengths 3 and 4 calculated. And since now the sum of 0 and 2 is available from the previous step, it can add that, resulting in the sum of the lengths 0 to 4, which is the final result actually for thread number 5, because that is exactly what we wanted. right? Note again in step 2, also here only half of the threads are doing something. But it's a different set of threads, right? Here it was threads number 1, 3, 5, 7, etc. Here it's 2 and 3, 6 and 7. And in step 3, it's again a different set of threads that extend the range of their partial sums, resulting now in all the alt offsets being ready after step 3 is completed. And here threads 4, 5, 6 and 7 were the ones that were participating. Now, how many steps are required to get to that result? Let's have a look. After step 0, we had only one offset ready, being offset 1. After step 1, 2 offsets were ready, being this one, and this one was complete. Now, after step 2, this one was also ready, and this one was also ready, so now we had 4. 1, 2, 4, 8. So it's easy to see that each time we do a step, the number of calculated offsets actually doubles. So the number of steps required is actually log 2 of the number of offsets required. Okay, we have now all the odd offsets. Let's calculate the even offsets. And also that is pretty easy to follow. If you want to calculate this 0 up to 3, basically you have to take that value, add length number 3, and you end up with the right sequence that is required for that. So in the final step, all threads are calculating something again, and they just do one other addition. Good, let's look what it would look like if we had again twice as many lengths in the RLE decoding. Well, you see, this pattern is actually what we had before, and there is a very similar pattern running next to it, and then we need one extra step here, step number 4, to handle twice as many lengths compared to the previous pattern. But of course, twice as many threads are also launched to get those results. Time for some code. Now, the first part of the code runs actually on the CPU. We have always like a main function here, and it starts with handling the buffers that are used to exchange data between the CPU and the GPU. So we start with the allocation of all the input data, that's done here, the length of the sequence, all the values, and all the lengths of the sequences, each corresponding, of course, to a value and telling the length of the sequence of identical values in the uncompressed sequence. Then what I did is generating a random sequence. That's nothing fancy, except that we get also the total length of the uncompressed sequence. And that's important for the next step, being the allocation of the buffer required to hold the uncompressed sequence. The GPU will put it there, and you need to allocate a certain length. It could be done differently. You could, in another way, add all these lengths, or send over the length or store somewhere the length of the uncompressed image of series, and then use that value actually to allocate the buffer. That's the first part of the code. Now, a little bit of explanation. We know that in the algorithm, each step actually uses partial results calculated by the previous steps, right? For this one, we actually uses something calculated by this thread and something of our own. And these are shared buffers, so that's available for everybody. But these partial results, they are not just available like that. Actually, what we need here is something that CUDA supports to exchange data between the threads or in between the threads, and that is called shared memory. Now, the size of shared memory is actually a parameter when launching the threads. You launch the threads with CUDA launch cooperative kernel, and one of the parameters of that function is the size of shared memory between the threads. here what we will use is one integer for each thread, and we have half of the number of sequences as the number of threads, so it will the multiplication being of those sizes. Again, a bit further in the code, you know that we will launch the threads here, and as always in CUDA, each thread executes the same function. Here that function is called Decode RLE, and we launch a number of threads being half of the number of sequences. We only use one block, and there is good reason for that, because shared memory is only shared within a block of threads. So we only use one block of this amount of threads. And the parameter to the function itself are actually defined here. And that is an array of pointers to all the allocated buffers. So the 3 input buffers that we defined, and then the place where to put the output. And then the last parameter is actually the size of the shared memory that we explained previously. All right. This call is important because after the GPU has done its work, then this call makes sure that the output buffer will be resynchronized with the memory in the CPU, so that the output result is actually available on the CPU. Let's look at the code that runs on the GPU. The function decode RLE. It has the 4 parameters that are passed to it. So the 3 input values and the place where to put the output. So each of these pointers is actually pointing to shared or at least synchronized memory. Note that the prefix here, global, that's the indication that this is a function defined to run on the GPU. And it's actually this function that will run simultaneously on all the threads that are launched. So each thread gets the same input parameters. And we will later see how each of these threads will know what part of the total set of tasks it needs to do by using an identification of the thread itself. So it's not by input parameters, but by an indication of the thread that we will know what to do in each thread. The start of the function is doing some initialization. We first read the length of the compressed data, and then we define a variable that points to the shared memory. So what you can see here is that the shared memory, you don't need to allocate it yourself, but it's actually done by launching the GPU threads and passing that parameters. And that prefix here makes sure that this array is actually using the memory of the shared memory that was created. Then we define a grid variable, and that grid variable will actually allow us later to synchronize the threads. And lastly, we get the unique ID of the thread, and that will help us later to do within a thread the work specifically for that thread and that thread alone. That's the initialization. Now we start with the algorithm. Remember, step 2 is already doing some partial sum of 2 lengths. For instance, thread number 2 calculates the sum of lengths 3 and 4. Now, that 4 is actually deduced from the thread ID. So thread number 2, there the even index is 4. For thread number 3, the index is 6, etc. So that's this here. And then the addition is done here. So you see that sum here. It's adding this length and this length. The only exception is in thread 0, because in thread 0 there is no value here, so there that's actually 0. But you see that this is an easy calculation. After that, it's important to sync the threads so that all sums that are calculated and they are stored in the shared memory when we continue the code. Because we will reuse those partial results. You see the beginning of the blue lines here. You will reuse those results in the next step. And for the next steps, we need to introduce something. We introduce the concept of groups. In the picture above, they are indicated with the colors green, blue, and red here. So they are groups of threads. These groups of threads, they have in common that they all use the same partial result from the previous step to their own partial result. So for instance, with blue here, in step 2, we see 2 blue groups. The 2 threads in the first group will both add the partial sum of thread number 1 to their own sequence. 3 to 4, 0 to 2, 0 to 4, 3 to 6, 0 to 2, 0 to 6, right? What we also see is that in each step, the amount of groups is only half of the previous step. Here there are 4 green groups, 2 blue groups, and only 1 red group. But within a group, the number of threads actually doubles, going from 1 to 2 to 4. So the total amount of threads that are participating remains constant. Now the amount of threads in a group, that's what we call group size, and that will actually be used to go over the steps. So the group size starts with 1, and it always doubles in each step. We use like a bit of a helper variable here that is the double already, because it's easier to use in the algorithm. But basically we double the group size in each step until it has become too big for the sequence. Now what you can also see is that in between the groups there are threads that are not doing anything. And that gap is actually the same size as the group size. And then what each thread needs to do is first look into what group it could belong, and simply using the thread ID divide by twice the group size, and that's because of the gaps, gives us that group number. And then in the second step, we determine the minimum and the maximum thread of that group. The minimum is actually with the group size and the group number easily calculated, and the maximum thread is that minimum thread size plus of course the group size and then -1, because otherwise you end up here. That's the maximum thread. So then the thread determines, am I participating in that group or not, as half of them will be not participating. And if the thread should participate in the group, we do actually 2 things. We find the value to add for that group, and that's simply the length right in 1 thread lower, right? And then we do the addition. After that, we need to sync again, because after that step, after each step, actually all the values are calculated and they need to be ready in the shared memory before we will use them in the next step. Now, after all these steps, we have the offsets calculated. Now for thread ID 0, the even offset is simply 0. We start at the beginning of the buffer. But for all the other threads, we need to use the sum of 1 thread lower to calculate the even offset, and that's actually what is done here. So we use, for instance, for this one, we use that value and that, and then we add up here. That's what is done. Now we put this in a small array because that will make it easier to do the next step. And that next step is actually filling the output buffer, and that's pretty straightforward. So we do it for the odd and the even, and it uses the value that it needs to use to fill into the output, and we do this for the length of the sequence. So looking at the full decode RLE function, we see it's merely 45 lines of code, some initialization, step 0, adding 2 values, then all the steps that each time extend the range of partial results with the previous values, and then the last step filling the even offsets before we can fill the output with the fully decoded RLE. Now this version of the code is not really optimal because since shared memory is only accessible by the threads of 1 block, and 1 block is actually limited to 1024 threads. This code is actually limited to 2048 sequences, which is a bit painful because we know that in the middle steps half of the thread is doing nothing. They are not belonging to a block, and that thread is actually limiting how much we can handle. Now we can at least double the amount of sequences by reorganizing the work amongst the threads. The code is a bit more difficult to understand, but also not that difficult. Perhaps I put it in another video. Thanks for watching, and refer to the notes to get access to the code on GitHub.